It's really such a pleasure to be here. I'm a graduate from the department from 2000, and I'm really excited to have taken over from Diane Finkelstein's role as the director of the Biostatistics Center at MGH. So I'm going to talk a little bit about, with my hat on as the MGH Biostat Center Director, but then also talk a little bit about my research and do that all in less than 5 minutes, so bear with me. I just wanted to mention that the Biostatistics Center at MGH has core support through several different initiatives across the Harvard system. So that includes the Harvard Catalyst, which is the CTSA, the Clinical Translational Sciences Award, the Dana-Farber Harvard Cancer Center, the Center for AIDS Research, as well as the MGH Division of Clinical Research. And we collaborate with, here I've listed a number of the groups that we work with. So we have collaborations with at least 15 different groups across MGH. So it's a very broad set of collaborations. You can see that ranges from psychiatry and pulmonary and critical care medicine to infectious disease, cardiology, anesthesia. So we have a lot of different projects and a lot of opportunity for engaging students in those projects if you have a particular area that you're interested in. So the work that we do includes our collaborations through those cores that I mentioned. We have research partnerships with each of the different groups. We also have a number of data coordinating centers that we're responsible for. So those are multi-site centers where we manage and analyze all of the data. So lots of data are coming through our center. And then we have independent biostatistics research as well. And that's what I'm going to talk about now, which is my own. We have several different individuals doing independent work in biostatistical methods, but this is what I'm working on. So this is funding that I have through an R01 award from the Institute for General Medicine at NIH. And it's called Integrated Methods for Omics Data. So the basic premise of this research is that when we have all of these GWAS, and I imagine most of you are familiar with, in some extent, with GWAS, we've found through these studies, the genetic association studies, relationships between SNPs and traits. So we now know that maybe a particular SNP is associated, or mutation in the genome is associated with a specific trait like cardiovascular disease, body mass index, and so on. What's not understood still is how we get from that SNP to the trait. So what the mechanism is in between the mutation that we see in the genome and the trait that we see. So this project is focusing on trying to understand this mechanistic pathway between the genes and the traits. And the reason we do that is because it can inform drug development efforts as well as precision medicine applications. So we'll be better able to develop new therapies as well as think about how best to treat patients if we really understand mechanistically what's going on. So specifically, we're looking at expression, so how the genes are expressed. And it's complicated for a couple of reasons, and I'm just going to mention those. The first is that we have what's called non-rectangular data, which means that we have some data in some data sets and other data in other data sets. So in a GWAS, we typically have the SNPs and the trait, and then in the transcriptome-wide association studies, we'll have the SNP and the expression, but not the trait. So we're trying to integrate these different data resources, and that can be complicated because of biases that exist in how the data are collected. So for example, the GTEx data, which is commonly used for looking at this SNP expression data, is all people who've actually already died because we need to look at brain tissue expression and other parts of the body. So obviously people who are died are different than people that are still alive that we're studying in these GWAS investigations. So how we put those together is a challenge. The other challenge has to do with the dimensionality, and I'm just giving one example here where we might be interested in understanding the relationships between SNPs and obesity. Obesity could be measured by body mass index or waist to hip ratio. Body mass index is thought to be a measure of overall obesity, and waist to hip ratio is something that is more more localized. So there's some understanding of this to raise the hypothesis that body mass index or overall obesity is controlled in the brain. It's related to addiction, for example. While waist-to-hip ratio may be more locally controlled. And just to add to that, it's further complicated by sex in this case, where we know we have different gender associations. So thank you. I wanted to just add, these are two pictures from my graduation here with Annie Herring and Debbie Chang. And this was my baby who's 19 now. Tonight, actually, she's down in Providence, but she came to my graduation.
Does anyone have any questions for Andrea?
Thank you, Andrea. Just, I know you've only been there for a little while. Are there opportunities for students there?
Thank you. That's the perfect question. So there's always opportunities for students, and we have opportunities at several levels. So if you're a master's student and want a project to work on, we have opportunities for short-term projects. We have opportunities if you're working on your PhD and you want to work longer, so and do some methods development work. There's also a lot of opportunities, and I'm creating them now as the new director a month and a half in, for graduates. So once you've graduated, or as you're thinking about graduating, if you think this might be an environment that you'd like to come to, please reach out. Here's my email address, and I'd be more than happy to talk to any or maybe not all. Thank you.
Thanks, Andrea. We have Jonathan Huggins up next. Sorry. Oh, you're right in front of me. Jonathan's a postdoc in the department working with Scott Carter and Jeff Miller. So thanks for coming.
Hey everyone, yeah, so I'm going to be talking about some joint work with Jeff on making Bayesian inference more robust. So I'm actually going to skip over that. We're going to go right to the fun part. So just going to talk about sort of an example, real data example here. So our goal in this example is to predict insurance claims that are going to have to be paid out in future years based on some historic data. Okay? And you know, I'm a Bayesian, so what do? I write down my model for how this data might have come about, and I try to, and I use the data I have. It's this actually non-trivial kind of time series, multiple time series data, and I try to infer what the future claims are that this insurer is going to have to pay out. And you know, this is great. I have some uncertainty shown in this distribution over possible future claims. And so that's great. I can, you know, the insurer can go off and make their decision about, you know, how much money they need to keep around so they can pay their bills. So that seems great. The problem is the model is wrong, and here's the true amount that they actually had to pay out. And what you'll notice is that, you know, Bayesian was pretty certain that we were going to be somewhere in here, but we're actually all the way over here, right? And the problem is basically that the assumptions baked into Bayesian inference, in this case, were not correct, okay? We assumed some relatively simple model for how this insurance and these claims were being paid out, but that wasn't correct. So what can we do? Well, you might consider doing something like something more frequentist like the bootstrap. We only have 10 observations here. I wouldn't want to do bootstrap with 10 observations. But what we can do is we can combine bootstrap, really bagging, which is bootstrap aggregating, and Bayes, and get something called the Bayes bag posterior, or bag posterior. And what's cool here is that suddenly we have a bunch of posterior mass on these smaller values, okay? And so our uncertainty is suddenly much better calibrated by using Bayes bag. So that's Bayes bag. I think it's a pretty cool method. We didn't come up with it, but no one had really sort of tried to figure out its statistical properties or really apply it to methodologically interesting problems. How much time do I have?
It's 2 minutes, 39
Okay, cool.
seconds.
So just a quick reminder of like what, so here, of what the bootstrap is, so I can define BaseBag for you. So here we imagine we have some true distribution P true. We'd love to be able to just draw more and more data from it, but all we have is our observed data, which are those little black bars there. But what we can do is we can form an empirical distribution and then resample data from that empirical distribution. So here's like a bootstrap data set where one observation we now have 3 times, and some of them we don't have at all, and one we have twice. Okay? And so the idea with the BaseBag method is we're just going to look at our posterior, that's pi of theta given the data, and for our data we'll take these different bootstrapped data sets, and we'll just average over them. And as you could hopefully see in that example, this works surprisingly well. So what do we show in this paper? Well, one, BaseBag combines this flexible modeling that Bayesian inference provides with the distributional robustness of more classical frequentist methods. Has some really nice, provably good statistical properties. It has really good empirical performance, which is obviously important. It's, theory is not enough. And it's really easy and it's widely applicable. If you have a posterior inference algorithm for your standard posterior, just apply it a bunch of times in a row. So it's really easy to use. And so in conclusion, you should really go out and give BaseBag a try on whatever interesting inference problem you're trying to solve. Thanks.
Does anyone have questions for Jonathan?
So what are the inputs to your model?
In that case, it was, in the example I gave, or in general?
Just like in general, like what do we need?
Just basically, so standard bootstrap, you have sort of independent observations, basically. One thing we're still working on is like time series and things like that. Yeah. Sorry, no, I talk a little too fast.
Sure, I'll ask a question.
Yeah.
So, I mean, in the Bayesian paradigm, you've got the likelihood and you've got the priors.
Yeah.
You're not saying that the priors are misspecified. The priors are whatever they are. You're just talking about the likelihood being
I'm
misspecified.
primarily talking about the likelihood, but of course, like,
So I want to just,
Yeah.
the likelihood up there, pi of theta, I mean, that's the posterior
That's
that's
posterior.
based on the misspecified likelihood.
Yeah.
And then you're just averaging over.
Yeah, because basically what happens is by using the bootstrap, you're introducing the sampling variability that isn't being accounted for by essentially your model-based uncertainty, which is
So
what you have.
the performance must depend upon the extent to which is the discrepancy between the assumed model that underpins the likelihood and whatever the truth is.
Sure.
If
So,
you've got a very, very big discrepancy.
yeah, I mean, you could sort of, I mean, it's hard to know with only one sort of example, but like here, right, I mean, obviously ideally, like, the BaseBag posterior would be like centered right at the true value. Like that's obviously what we'd love to see, right? Oh yeah, we knew exactly what's going on. But yeah, you're kind of limited by how good your model is. But the nice thing about BaseBag is it can help you actually diagnose that your model is wrong and maybe help you fix it too. So that can be another good thing to do, right? If you're, yeah, it's nice when you have like a prediction problem like this. But if you're just say doing parameter inference and you don't have any ground truth, then this can also provide you with some diagnostics to figure out that there's an issue with your model. Yeah.
Can you do some kind of power analysis based on some assumptions on, for instance, how far away you are from the true model? Because it seems to be great that you can do something with 10 samples, right?
Yeah. So what we have, so we don't have any theory for the finite case really, except in like simple Gaussian models. But we do have sort of nice asymptotic theory about sort of the behavior of the like asymptotic variance and how that behaves. Yeah. But we'd love to have more non sort of finite sample theory, but that's obviously hard to do. Yeah.
So great, thanks, Jonathan. We have Sharon-Lise Norman up next. She's a professor of healthcare policy at the medical school and a professor of biostatistics in the department.
So I'm gonna take your unused time, by the way.
Yeah, you're 40 seconds.
Yeah, so, and I forgot I was giving this presentation today. This is my work day in my office, so this is why I look like this. So, I just wanted to let you know that first of all, I'm Canadian, if you couldn't guess by the slide. And, my methodological areas are causal inference, Bayesian inference, item response theory modeling, and usually in high dimensional data settings. In terms of substantive areas, how these methodological problems are motivated, it's really in the area of health policy, comparative effectiveness. I look at the diffusion of new medical technology, quality of healthcare, and regulatory science. Where is my office? It's 5 minutes behind you in terms of walking out the door. So what are some regulatory science problems that I have been working on? So one is medical product entry with the Food and Drug Administration, and mostly in the area of medical devices. So how does a new device come on the market? The most challenging part to medical devices relates to the surveillance of them, because unlike drugs, there's no specific unique identifier for medical devices. It was implemented in 2015. So if you have a hip replacement and that was done in 2010, it's very difficult to know which type of hip was implanted in you. The other types of problems I deal on sort of insurance coverage for medical products. So a new device may be approved, however, whether or not your insurer is going to pay for it is not de facto certain. And in particular, I do a lot of work with the Center for Medicaid and Medicare Services. That's people who, the government insures poor and those older than 65. They have a big population, so how do you determine whether products are important or not and worth the benefit? I also do work in transportation safety, and that's looking at the safety of motor carriers. And this is in the relation to profiling, which Sebastian does. But what I have been doing for a while, and that's looking at the quality of healthcare delivered to specific populations. What does that mean? I'm going to show you an example in a minute, but who's interested in assessing the quality of healthcare that's delivered? You know, is your hospital a good hospital? Is your doctor a good doctor? You know, should that hospital be open? Specialty societies are interested, so the American Heart Association, the Society of Thoracic Surgeons, they're interested. The insurers, the Center for Medicaid and Medicare Services, employers are interested when they go and negotiate for your health care. They negotiate with Blue Cross Blue Shield, whatever, and they're going to determine are the entities that they contract with good providers. So that's a very quick description. But I'm going to give you an example that I'm working on now. And so, is this a big deal? It might sound like a snore. We're looking at the quality of health care. Actually, it has a lot of impact in terms of populations. So I'm trying to think now, was it in 2013 or whenever it was, but there was a big deal at All Children's Hospital in Tampa with problems with their quality of their pediatric cardiac surgery. Little children were dying, pediatric kids were dying, needles were left in their hearts by accident, they weren't told, people weren't doing things that they were supposed to do, and this mounted over several years. John Hopkins owns that hospital, and they have to pay nearly $40 million to two families hurt by this. In addition, the state of Florida has penalized the hospital in the amount of $800,000. So the question here is, and this is a particular problem I'm working on now, is what is the quality of surgery for pediatric and congenital heart disease patients? And we're going to look at all-cause mortality. And also, which management strategy is best? You can think of it as which treatment is the best, and we're going to have 1,000 different treatments. So if I give you some context, there are about 35,000 surgeries, pediatric surgeries, cardiac surgeries in the US. There are about 200 hospitals that provide these types of surgeries. The surgery is very complex. You can think of a premature neonate needing cardiac surgery. This is very complex. And there's multiple stage procedures within a single operation, and there could be multiple operations within a single admission. The relationship between the type of procedure and the underlying diagnosis with mortality varies. So we have about 42,000 possible diagnoses combinations, and about 3 35,000 possible procedure combinations. So that leads to about 100,000 possible combinations. We've got 35,000 children, 200 hospitals to try and disentangle a good hospital from a bad hospital and what treatments are best. So in terms of what are the statistical problems, we have a sparsity problem. If we just examine all the natural occurring diagnosis procedure combinations, it's about 3,000. That's not that big. But what about the risk factors? This is not randomized. And I have 2 minutes, 40 seconds. There are hundreds of covariates. It's a causal inference problem. Is hospital A good? And finally, it's a clustering problem. We have a lot of subjects within centers and surgeons and patients within centers. And currently, right now, we have about 100,000 observed children for a certain period of time. So thank you.
Someone have questions?
I was wondering, also have data on, someone who's not treated, even though, because this is now, treatment went bad, right? So there were mistakes.
Oh, no, treatment went good too. So this is all surgeries.
Okay, all surgeries. But there's nothing on, because I had the impression, it's pretty difficult here to get treatment, once, to even get admitted to see a doctor. And there might people, maybe die on the way because.
Oh, sure. But yeah, so no, we don't have this. We're assessing the quality of cardiac surgery that was done. But you're absolutely right. Usually with neonates, they're in the hospital. They're there to. They're not going to be discharged. And they're just. But certainly some could die from out of home. So.
Like it's just you and me asking questions. So do you, just in a 1 or 2 sentences, do you have a framework for how you're going to address all of these problems? Or,
Well, I think some students should come up with some suggestions.
so there are opportunities for students.
Lots of opportunities. But I'll tell you what we've been doing. We just started this project maybe 8 months ago. So the first task is we have a panel of cardiac surgeons that are trying to look at the 2,700 combinations. Is there a way to combine them a little bit more? And that's, now we're down to about 800, I think. Now that's it, that's as far as they're gonna go. So now we have to think about how are we gonna model this? And we're sort of thinking right now maybe random forest. We need to think about some high dimensional things because I didn't talk about the chromosomal and the syndromes, congenital, they all interact. So it's highly interactive. So some type of data approach that you're going to have to induce some regularization somehow in order to deal with that. And then we have the usual question of causality. We might do template matching if you want to look at a common set of populations. So we're thinking about that. And then I haven't even touched the comparative effectiveness problem. So is, out of those 3,000 combination, is number 1 better than number 2? Those types of questions. So it is ongoing research, open up to lots of different problems. There's missing data, there's high dimensionality, there's and differential error associated with the information. Because we have genetic information, we've got the usual demographic information, we have pre-admission risk, so lots of different types of data with lots of different error distributions. So.
I'm wondering regarding your clustering problem, if there's you're seeing like a relationship between the size of the centers
Oh, absolutely.
and the quality of care.
Yeah. So that's a common, if anybody forgot, I hope not, needs surgery, go to a place where they do a lot of your surgery because volume is usually related to that. So you actually raise an important question, and that is, we'll do some hierarchical modeling or something to address the clustering. But the other thing that remains is there are going to be some centers with small numbers. How are we going to be able to assess the quality of care when there's not enough sample size to do that? And so thinking about ways to try and get some inference that isn't so uncertain is a really important problem. But for payment purposes, every hospital has to be assessed. So even if you only treated, you know, this is surgery, there's gonna be a big cluster, but there are some hospitals with very few patients. So, oh, Paige.
So, it sounds like what you're doing is sort of like retroactively looking at this bulk of data and trying to assess patterns, but, when this issue came up in Tampa, do they reach out to statisticians and say, like, can you explain what's going on? I know there's this issue right now with premature babies, I think in one hospital in Pennsylvania, Philadelphia or something,
Yeah.
being transferred to a different hospital because they suddenly realize they are having a problem.
So-
Do they contact you and say?
Well, they contact the Society of Thoracic Surgeons because that's the society. These data come from the Society of Thoracic Surgeons, so they contacted them to see what was in their data.
Mhm.
I wasn't involved.
Yeah.
They came to me afterwards. There is a site review. I don't think there's any there's no statistical modeling per se. They go through, and I've done this in
Yeah, I just
Massachusetts.
wonder what happened with like acute crises when they have.
Well, I can tell you what they do in Massachusetts, because I monitored the care in Massachusetts, so if there's a problem, the first thing that happens is the hospital's notified. The director of the Department of the Health Department needs to decide whether or not to close the program, whether or not to suspend the program. If you close a program, it may cause other programs to close. So you need to find, I'm taking too much time, so I'll make it quickly. And if you close a program, it may be the only program serving, it might be a rural program, so you need to think about that. Then they usually ask for every death, all the medical records for every death. So it's really done on a real detailed basis, as opposed to, thinking about it in a broader context.
Thank you so much, Sharon. And lastly, we have Boyu Ren, who's a postdoc in the department as well.
Thank you. Hi everyone. Today I'm going to talk about multi-study learning for prediction, and hopefully I can make it in time so that we get to the alcohol as soon as possible. Okay. All right. So first, let's introduce what is multi-study. So the idea is that usually when people are trying to study relationship between an outcome Y and a bunch of covariates, you would have access to more than one study. So here you have 3 studies. But the thing is, usually these studies are not exactly the same. So for example, some study they're looking at a very limited region of the covariate space, and sometimes the relationship between Y and X might change from study to study. So basically, you have to really acknowledge these study heterogeneity when you're doing any learning task. You cannot really just merge the data and train a single model on that merged data set, because they're not exactly the same. So that's the multi-study setting. And the learning tasks we're focusing on today are basically 2 tasks, and they're all prediction tasks. So the first one is what we call generalist prediction. So by saying that, we're basically saying that we construct a prediction model based on all data we have, and we want to make that model to have good prediction performance on a new study, which is not really observed. And if that's possible, usually you would assume sort of there is some connection between this new study and the existing study. For example, we have a hierarchical model. And the other task is what we call specialist, and this is really straightforward. So the idea there is that you want to do good prediction for new samples in an existing study. For example, here we have study 2. So the idea there is that you can really borrow some information from study 1 and 3 to help you improve your prediction model, which is trained only on data from study 2. Okay, so that's the learning task. So the way how we approach these 2 tasks is that we're going to focus on a very specific type of model, which is called stacking model, which is very straightforward. So this type of model basically uses linear combination of study-specific learner, like so here I say them as f hat k. And lambda k here, you have to really tune it towards sort of like the learning task you are doing. So for example, if we're doing generalist prediction, this is the type of utility function that you want to maximize. So this small u here is any type of utility function, for example, negative square error. And so this is basically saying now what's the difference between your stacking predictor and your observed value. So, and also we have a nu here. So nu k here, which we call a mixture weight for study k. So that can be really interpreted as the probability of the new study to be more similar to the existing study k. So that basically you are saying, like, if I sample many times the new studies, then out of 100 times the new k, you will have some study that is very close to study k that you have already observed. So we have another term, which is the penalization term, and that term is basically to take care of the linear correlation, the high correlation between those fk hat, because they're trying to learn basically the same relationship between y and a bunch of covariates. And also, if you do a specialist prediction that's really straightforward, you just use data from the specialized study, which is study 2 here, and then you evaluate your stacking predictor. Okay, so this is like one major contribution to our method, but I'm going to quickly go through it. So the idea here is that the two target function that we introduced before actually has some drawback. And one of them is that you actually use your observed data twice. In the first place, you use your data to train your FK hat, and then you use your data to identify those W. But that leads to basically too optimistic evaluation of your prediction performance, and which is not really optimal. So in order to alleviate this issue, what we propose is that we propose a cross-validation type of algorithm, so that basically before here the summation is over all k prime from 1 to 3. But here we modify this summation such that if you are looking at data from study k, you don't really involve the model trained on the same data set, but only use the other two studies. And then you have to have a scaling factor to actually bring down the bias by doing this. And eventually you also have the same sort of weights for the new studies and also the penalization term. So the reason why I call this zero out is because actually this new target function is equivalent to say that when you evaluate the performance on study k, you will set the prediction value of fk hat to be exactly 0. So like what we are doing here. So this is the standard stacking. So this is your outcome, and you have 3 covariates, which correspond to 3 models. And then you do the regression to get your W. And zero out is basically the same, but then you set the diagonal piece to be exactly 0 to reflect this sort of summing over k that's not equal to k prime. And that will give you exactly the same as the solution of this. And we can actually prove theoretically that the zero out has better prediction accuracy than regular stacking. And I think I will just conclude here and take any questions.
Anyone have questions?
It seems like coming up with these new k weights is non-trivial.
Oh,
well.
you mean this like to?
No, the new k is in.
Oh yes. So usually you would say probably I don't have really any prior knowledge about the new study. So I would just say they're kind of all the existing study kind of exchangeable. So I just set the new k to be 1 over k, for example. But sometimes you would have some prior knowledge. So some, if you say the new study are more close to one of the existing study, then you should assign more weights to that existing study, or the W for that study. Yes.
So to me, it seems really intuitive that the zero stacking would do better.
Yeah.
So how much better does it do? Like, can you quantify that? Like,
So,
just to say it's better, is it like, 2% better, or is it like 20% better?
That's a good question. So we don't really have a theoretical result, but we can show is like the difference between like the performance of the regular stacking and the zero out stacking is always positive or non-negative, but we don't really know how what's the the rate of that as a function of k, or the number of studies and the sample size. Mm-hmm. Yeah, maybe that's the next step that we should do, actually. But it's kind of difficult, actually. Yes.
No, you get
Yeah.
I was just wondering, so when do I understand correctly that zero stacking would mean, you basically, you stack your data and then you do cross-validation based on your full data? because I'm wondering, just do you have an intuition why this is supposed to be work better? Because I
Oh,
would
yes,
assume
yes,
if
yes,
you-
of course, yes. So the intuition is actually easy. So if you're doing this, so basically the evaluation data set is YK, whereas the training data set is one, so for example, like, let's say K is 1. And that term is going to be Y1, and this summation is F2 and F3. So that basically said that the training data is study 2 and study 3, whereas you use study 1 as your evaluation data. So there's no overlap. And that basically works as what we're doing in cross-validation, although not exactly the same, but in a similar spirit. So that's the reason why we have the better performance. And like if you want to do it like more analytically, you can actually rewrite this utility function as a penalized version of the regular stacking. And you can see that penalization term is actually shrink the W towards a specific value, which kind of like what people do in, it's kind of like what the Stein estimator is doing. It's basically depend on the ratio between the mean and the variance, and then you try to subtract that from your model average. Oh, sorry, sample average, yes.
I see that, but why is it better? Like, let's say I take 1/3 of one data, 1/3 of the other data, and 1/3 of the other data.
Right.
I hold them out,
Yeah.
as my whole data, and then I train on the rest, which means I get data, I get information from all the data sets.
Yes, I see what's your point.
This gives me, more information about the data distribution tomorrow.
Yeah. So the thing is, if you construct your evaluation data set using that form, that basically saying you're considering that the new data set is kind of like a mixture of all those 3 data sets.
Yeah.
But I think we have a parameter new k there for doing that, I think. So I think there shouldn't be a difference between the way that you select like 1/3 of the data from each study and use them as evaluation, as opposed to doing something like this. And also this is easier for training actually. This is much faster than doing that cross-validation type of thing, because you can just do this kind of trick.
Because you don't need to learn your perfect petition somehow.
I'm sorry?
Because you don't need to learn, because I could also imagine I learn now petition, right?
Yeah.
So I want to somehow, let's say I want to have 3 groups.
Right.
And I learn them, right? And I want to learn, which data should go in which group.
Yes.
So that I get my perfect, that I get the best possible prediction performance. But you're kind of saying that the best one is really that I, that I keep my original independent data sets?
Yes. Yeah, so that's the idea there, yes. Yeah. But I think there is also some work, I think, from Ben. I'm not sure if it's Ben here. He's right there. And he is doing something like what you just described. He will construct a synthetic data set that is basically like a mixture of existing data that is close to the target that you want to do prediction for the future study. And so in that case, I think, so like his method is particularly tailored towards that type of optimization strategy.
When you say accuracy, what do you mean? Are you talking about variance? Are you talking about efficiency?
Yeah, so here, this accuracy here, I'm talking about mean square error. It's basically like variance plus bias, and the reason, the reason why this works better is because it trades bias with to variance.
Plus,
So.
it's Stein, right?
Yeah.
So if you had 2, K equals 2, do you follow Stein? I mean, if it ends up, it doesn't work in certain settings, right? It has to be.
Yeah, so it's not exactly like Stan, because like
Yeah,
in Stan's estimator, you have to have dimension like larger or equal to 3, right?
That's right.
Yeah, but here, so the shrink, so the amount of shrinkage this thing has actually depend on the quantity you're trying to estimate. So it's not exactly like a estimator, but we're talking about like taking expectation of the thing you're estimating, and then eventually it goes, it behaves like a Stein type of shrinkage, or yes, so that it has better performance. Yes.
So I have a question about the specialized case. So you said in this case, like we are thinking about inference problem, but we are also trying to use the information from other
Yes.
data sets.
Yes.
And so the definition you give for lambda g hat, so like I think it is the previous slide or the slide before that.
I'm saying, talking about this one, right?
So like how the other data sets, like they are helping here because only the second data set is in the definition. Is it
Oh,
true
that's a very good catch. Actually, so if you just use the whole data set to train one F hat in this process, you can really not do 0 out for the specialist prediction, because you will just take we were basically just using model 2 and model 3 to predict model 1. And so in reality, this method actually also do another step before all the training, another step of subsampling. So it will subsample each study into smaller into smaller data set and train model on those smaller data sets. So it's kind of working like a random forest. It tries to decrease the variance of the final prediction. And in that case, if you do subsampling, then the zero out will work with specialists because you only take part of the data from the study you're specialized on. You can still use the rest of them to do the evaluation.
Thank you.
Thank you.